So friends, the speaker of this session is Dr. Anupam Shukla. I would like to introduce him. Dr. Anupam Shukla is a professor in Department of Chemical Engineering, IIT Delhi, and has been faculty member of IIT Delhi for last 15 years. Professor Shukla completed 5 years integrated MTech in chemical engineering from IIT Bombay and PhD from IIT Kanpur in 2004. He then worked as a faculty member at IIT Guwahati for a little more than 2 years before moving to IIT Delhi. Professor Shukla works in the area of chemical systems with focus on electrochemical energy storage, mainly supercapacitors and batteries. The areas of interest further includes the membrane electrolysis, electrodialysis, electrochemical route to graphene synthesis, and ion exchange membrane. Professor Shukla has supervised 7 PhD theses and currently have 5 students working in different areas of electrochemical energy storage. He has published more than 50 research papers in reputed international journals and several in conference proceedings. Regarding the professional activities and awards, Professor Shukla was awarded that outstanding Young Faculty Fellowship from 2008 to 2013 from Indian Institute of Technology, Delhi, and Best Industry Related PhD Thesis Supervision in 2009 by FITT IIT Delhi. So, with this brief introduction, I request Professor Shukla to start this lecture. Over to Professor Shukla.
Thank you, Professor Pandey. Let me start by welcoming all the participants and thanking you for giving me an opportunity to give a talk here. And as you mentioned, the talk will be on supercapacitor, which is one of the prime areas of our research. So what we will do in this talk is, let me start sharing the screen. And what I will do is, just to preserve the bandwidth, I will just switch off my video so that the voice is clear. I believe you can hear me. Professor Pandey, could you please confirm that I am audible?
Yes, sir, you are audible.
Okay, thank you. So I've shared my screen. I believe it is visible to you.
Yeah, it is visible now. It is visible now.
Okay, thank you, Professor Pandey. So, as Professor Pandey introduced, I am Anupam Shukla in Department of Chemical Engineering, IIT Delhi, and among other areas of our interest, we have been working in the field of supercapacitor for last several years. And what I'm going to do in this talk is to give a very brief but a very fundamental introduction to the capacitor, which is at a very basic level, at beginner's level. And so some of that may be of, it will be of the nature of repeating your what you already know. But the idea is that everybody could understand. So the first part of the talk would be introducing some of the features and the working principles of supercapacitors, or electrochemical capacitor as they are called. And then in the later half of the talk, I'll be presenting two of the works that we have been doing in this area, just to give a flavor of what kind of research goes on in developing better supercapacitors. Okay, so let me begin. So essentially, supercapacitors or electrochemical capacitors are in the area of electrochemical energy storage. Okay, so energy, we all know, is one of the very fundamental key requirements of modern societies. All our daily work, most of it is automated, and all of it requires energy. So, of course, one has a supply of energy from mostly coming from what are called as heat engines. So we burn fuel, and somewhere there is a turbine which is run by a boiler if it is coming from burning of fuel, or it's hydroelectric power, but mostly the major portion of the energy in electric form is generated via burning of fuel. And when we do that, follow what is known as a heat engine path, then the energy efficiency, which is the amount of energy which is released on burning of fuel, to what gets converted into work, which is equivalent to the net electrical energy that one gets, is limited by what is known as Carnot efficiency. I believe all of us are aware of it, and that depends on ratio of the temperature at which the heat is ejected to the temperature at which heat is generated. And you cannot reject it to a temperature lower than the ambient temperature. So that limits, and also there are limitations on how high temperature can be of heat generation, because there are material limitations. Also, there is a fixed temperature, adiabatic flame temperature, above which one cannot go, whatever one does. So as a result, all these processes are limited by Carnot efficiency. And usually this Carnot efficiency itself is in the range of around 60% for the kinds of temperature that we use. And on top of that, there are inefficiencies associated with actual operation of the process. So thermodynamic efficiencies are never achieved in real life. They are kind of upper bound. And so the real efficiency that one gets, for example, if you're running a vehicle, would be in the range of 20 to 30 to 34, depending upon if you're running a two-wheeler, small engine have lower efficiency, diesel engine, higher volume, have little higher efficiency, can go up to 30%. Okay. On the other hand, so all of this is chemical energy. Please remember that the energy is coming from what is called as chemical form of energy. So energy stored in chemical bonds. So for example, if petrol is there, one can represent petrol is a mixture of alkanes, but one can represent it as octane for simple analysis. And so it is all CH bonds. And when it is burned, what happens is that CH bonds break and one forms CO bond, so give carbon dioxide, and HO bond to give water. So essentially energy stored in CH bond is not all captured in CO and HO bond, and the balance energy is released. So this is what is called as chemical form of energy, or using chemical form of energy. Okay. Now electrochemical energy storage, as they are called, are devices which again utilize chemical form of energy conversion. So essentially at the very basic molecular level, fundamentally the process is same. There is some energy stored in the bonds. We form new compound. So basically we break bond, form new bonds, and new bond can hold less energy. And so the balance energy is released. But however, what is done in electrochemical devices, energy storage devices, energy conversion and storage devices is a more complete term, is that this energy is directly converted into electric form by using something which is called as an electrochemical route. And when this is done, so we'll not go into details in a talk like this, but essentially it's an indirect process where the fuel doesn't meet the oxidant directly, but it gives its electron to an entity which is called as electrode, and the oxidant takes the electron from the other electrode, and the device that we generate having two electrodes is called as the electrochemical cell. Okay, so it's a process where chemical form of energy is converted, but electric flow of current is involved, therefore they are called electrochemical. Okay. And it turns out that when we use electrochemical route for energy conversion, then the efficiencies are very high. We are not limited by Carnot efficiency. Principally, one can go to energies which is essentially ratio of delta G over delta H. Okay. So with this background, essentially these are devices which convert energy very efficiently. So they can store energy in an efficient way and deliver it in an efficient way. And there are various electrochemical energy conversion and storage devices. So what is shown here on the left plane are some of the basic electrochemical devices. For example, batteries, and for example, lithium-ion batteries are given. There's another electrochemical energy storage device which is fuel cell, and then there is a class which is called supercapacitor. So these are three major, but there are others also which can be categorized as electrochemical energy storage device. What is common common in all electrochemical energy devices that the output is in electric form. So output is, though they work differently, but the output is always in electric form, and therefore they are very suitable for devices which require their own energy supply system, and the devices are not very large. So for example, all your portable electronics, laptop, mobiles, they which need to be carried to places away from the home electricity supply points. Since they need electricity supply, and device which will not have, which is small and can be incorporated, does not add much weight, electrochemical energy conversion devices are of the choice. So in fact, development of batteries and other electrochemical devices was primarily because of portable electronics. But now when the technologies has evolved and the energy density that they can, or amount of energy that they can carry has become large, they are also finding applications in other processes or other appliances or other applications, and one of the prime example is now move to the electrical vehicles. Okay, so that's the background of electrochemical energy storage. In nutshell, these are devices which convert chemical energy into electric energy, and they can do it repeatedly. So one of the things to also remember is that they are not primary source of energy like fuel is. Okay, so they are mostly secondary source of energy. They need to be supplied energy, and then they will store it, and when required they will provide energy. By themselves they don't generate, in the sense that they are not primary sources of energy. Just to begin a bit, so our talk is focused on supercapacitor, and if we look at applications of supercapacitor, these are some of the more cited applications. One of the most cited is they are being used as emergency to power supply for emergency doors in A380 aircraft, but they have also been shown to be used in buses or in boats to run these buses and boats. So sometimes as only supercapacitor energy supply devices, sometimes supercapacitors are used in addition to batteries, and they actually aid in reducing the amount of battery that is required, because they can get charged and they can deliver charge much faster than battery. So they can take care of spikes in the power requirement. Otherwise, one has to put very large amount of batteries to get these kind of. There are others, of course, several others applications, but we will not go into those in detail. So what is a capacitor? To begin with this background, what I'm going to do in the next few minutes is to basically start from the very basic. So capacitor.
I looked at all my politics in IS, ideas, efficient, and they don't do it. If there is something in case
There's some background noise.
yes.
Okay, so
All the participants are requested to mute their mic. Okay, sir, continue, please.
yeah. So capacitor, if you recall from your school days, okay, is a device which can store energy in electric form. So remember earlier we talked about electrochemical conversion, which is chemical form converting to electric form, but a capacitor, at least the conventional capacitor, stores energy all along in electrical form. There is no conversion of electric to chemical or chemical to electric. So dielectric capacitor, for example, the one that one sees in our ceiling fan, are dielectric capacitors. They always store energy in electric form. And what is the characteristic behavior of a device that shows capacitive behavior is that the amount of electric charge which is stored is proportional to the voltage that the device generates. Okay. And of course, if this proportionality is hold for the entire domain of operation, then this proportionality constant can be written as C, where C is called the capacitance. So capacitance basically characterizes a capacitive device. That's the most important variable telling about what the capacitor can do. Here is a schematic of what are called as electrolytic capacitors. So those are conventional capacitors with highest capacitance. Essentially, the device is that you have two layers of charges separated by a non-charge conducting medium. So there is a layer of negative charge and there is a layer of positive charge. And when one gets this kind of situation, then essentially it is storage of charge. There's a potential that develops across it, and then this device can be used to supply energy. So when this is connected to a load, the positive charges will flow onto the load, get to the negative electrode, and neutralize the charge, and that is how the device gets discharged. If you have to charge it again, then one connects to energy supply, one plate gets positively charged, the other plate gets negatively charged. So that's how they can be used repeatedly. Now coming back to how much energy they can store, so the amount of energy they can store is the CV square by 2, where C is the capacitance of the device and V is the voltage. Okay. If you look at what is the energy stored by these devices, for conventional capacitor, the energy stored is pretty less. And that has to do with the fact that the capacitance of these devices is very small. So how one can improve the capacitance? One is that the capacitance is inversely proportional to the distance of separation of the charges here. So if this is the distance of the separation of charges, then the capacitance of the device is inversely proportional to the distance. And what happens is, in the conventional device like aluminum foil electrode based electrolytic capacitor or dielectric capacitor, we basically have two conducting metal plates separated by a dielectric. It could be polymer or it could be aluminum oxide in electrolytic capacitor. And when this kind of an arrangement is made, then the distance of separation cannot be reduced beyond about micrometer length. If one tries to make device where the length is made into nanometers or fraction of a micrometer, then usually because of the roughness of the surface and manufacturing defects, some kind of short circuiting takes, and that's a very dangerous situation in capacitor because they can supply energy very fast. So usually it will lead to some kind of bursting, and therefore these devices are limited, conventional capacitor, with D in the range of 1 micron to a 10 micron. And when that happens, the capacitance usually that is obtained is about 10 microfarads per gram for conventional capacitor. Okay. Now, for example, the capacitor that is used in our ceiling fan, so I believe that most of us have encountered that during operation after some years, the speed of the ceiling fan becomes slow, and usually the rectification is that the electrician comes and changes the cylindrical unit, which is essentially this dielectric capacitor. And by the way, the amount of capacitance in that device is also in the range of 1 to 10 microfarads. So that's how low the capacitance is, but then this capacitance is still useful to run many of the electric circuit, electric appliances. So they fit the bill there, but where it is required to supply more energy, conventional capacitor face challenges, and one of the challenges, just to give an example, is apart from energy supply, capacitors are also used for filtering. So all your electronic devices, the transistor runs on direct current DC, while the supply is AC. Okay, so the AC is converted to DC, there is a rectification, and when rectification is done to make the voltage constant and avoid ripple, there is a capacitor which is placed, which is what is called as filtering. So all our electronic devices will have a signal processing unit or a filtering unit, and the electronics, while the other parts have miniaturized to a greater degree and are very small, usually the biggest size in the device is this AC to DC converter, because the capacitor which have to be used cannot be miniaturized simply because the capacitance is low. So that's one example of telling that there are requirements where if we have high capacitance, then there are a lot of market for it. Now, with this, how can one improve or increase the energy density in the capacitor, essentially increase the capacitance? So there is a structure that develops which is called as electric double layer. So what we will do is explain using this schematic here. So consider just the right part of the figure here, which is called as the bulk solution. So essentially the idea is that I put a metal conductor or an electron conductor into a ionic solution. So there's a liquid containing ions, cations and anions. And if I put a salt into water, for example, it will break. For example, common salt, if I place, it will break into Na plus ion and Cl minus ion or chloride anions. And if I take any small volume, however small volume I take, which is of course larger than the size of the ions, then the number of positive charge because of cations is same as the number of negative charge because of anion. And the solution therefore is electroneutral at all length scales, which are larger, sufficiently larger than the size of the ions. Okay. However, if I place a solid, and connect this solid to some electric supply so that this solid attains a positive or a negative charge on its surface. So when that happens, then the liquid responds in a way to compensate for the excess charge that it sees on the surface of the solid. Okay. And as a result, what happens is some of the region near the solid surface becomes charged. So liquid side of the system close to the solid surface also becomes charged. And of course, there are different layers of charge, but essentially the idea is that some part of the liquid also becomes charged. So essentially now what you have is you have a positive, for example, to be specific here, a positive charge on the solid side, and there is a negative charge on the liquid side. So it is similar to the arrangement that we have seen here. Okay, this is like the solid charge and the liquid charge is on the left side. The only difference is while in this completely solid state device, the charge are confined to very small thickness and therefore one can model them as if they are confined to a surface. In this structure where you have a solid and an ionic solution, the liquid side of the charge is little distributed. So there is some average distance where the negative charge for modeling purpose can be thought to be as located. So essentially what we get is we again get a charge separation, a positive charge on the solid side, a negative charge on the liquid side. And remember that this is only for to keep the discussion specific. If I charge the solid as negative, then the liquid will respond by making the layer close to the solid as positive. So positive, negative, therefore can be interchanged. And this distance of separation that one gets, so this is called, this structure which develops is called as electric double layer. Okay, and the electric double layer, the positive charge to negative charge separation is in nanometers. To give an example, the thickness of electric double layer, if you have 1 millimolar solution is about 30 nanometer. If you go to 0.1 molar, it's about 5 nanometer for a univalent salt. So that's how small the thickness is. So basically, EDL therefore also will show a capacitive behavior, except the fact that the distance of separation between the charge will be at least 1,000 times smaller than the dielectric capacitor. So by simple understanding, essentially an EDL capacitance per unit surface area will be at least 1,000 times the capacitance that one can get in solid state device. Of course, what happens is the capacitor, so there are capacitors which are made on this principle and they are called as electric double layer capacitor, EDLC for short. Okay, and that is one type of supercapacitor. So that's how we get into from capacitor to supercapacitor. And actually it turns out that for good materials, the capacitance can be as high as 100 to 500 faradays per gram. Now compare this with what we put in the previous slide for solid state capacitor, which is 10 microfarads per gram. Okay, so obviously this is not 100 times, not 1,000 times, but much more times than what we have shown in the previous slide. The additional order of magnitude improvement comes because the material which is used in electrode for electric double layer capacitor has lower density than what is used in the solid state device. Second thing is, remember this is again a surface phenomena. So if I increase the surface area, then I get additional increase in the capacitance. So in the electric double layer where you have liquid, it is possible to consider electrodes which are porous. And when you get pore, because the electrolyte can enter into the pore, okay, there is not much that one can gain in a completely solid state device by making electrode porous. On the contrary, one will only lose there because the conductivity will go down. But here, by making the electrode porous, the surface area can be again increased by 3 to 4 order of magnitudes, okay, or even higher. So therefore, both of these combine to give very large increase in the capacitance. And people have reported 100 to 500 Faradays per gram for various types of material. In fact, the reports are even higher, as we will see when we proceed into this talk. So what is essentially electric double layer capacitor? Now, one of the things to notice is if you have to make a device out of this. So electric double layer, as shown in the schematic here, there's a positive charge on the left hand side, which is solid, the gray colored thing. The blue color is the solution, and then one gets a liquid side charge layer. So this itself becomes a capacitor. Okay, but if you have to use only this part of the device, only the left half part of the device, then how is one going to connect the external circuit to the liquid? Because one will require a solid to connect to the liquid. As soon as we enter solid into the liquid, it will also behave like an electrode. Okay, because it's that solid which is used to connect the liquid side of the charge is no different from the solid on the left hand side. Okay, so essentially any independent cell. A cell is the basic minimum unit that will supply power to the external circuit. Okay, so for EDLC, one of the flip sides or the disadvantage is that even the smallest unit will have at least two capacitor in series. Okay, so when we connect two electrode, insert into the liquid, form a cell, there will be two capacitance at least, one at each electrode. Okay, so essentially the smallest cell consists of two capacitance in series. And as we all know from our school book electrostatic, that the equivalent capacitance in case of capacitance in series is harmonic sum, which is less than the value of each one, which is what is shown in this equation, that 1 over C EDLC, so that is the capacitance of the entire device, is 1 over the capacitance at one electrode and 1 over the capacitance of the other electrode. And so therefore the equivalent capacitance will be less. So that's one of the flip side that comes in. We are not including this discussion in the talk for the sake of time, is that although we have shown that there is only one capacitance at the electrode, at each electrode, essentially there are multiple. So to get back to this situation here, the electric double layer itself is not a homogeneous structure, consists of multiple parts. One of the part, which is called as compact layer, actually has ions which are more or less immobilized, not moving. And the other part, which is diffused part of the layer, the ions are diffusing or moving around. Okay. So each of these layers essentially will be considered as a negative charge facing a positive charge. So this itself is a two capacitance in series. One because of the compact layer on the liquid side, and the other because of the diffuse layer on the other side. In fact, what happens is, the compact layer itself consists of two planes at least, what are called as inner Helmholtz plane and outer Helmholtz plane. I don't want to burden you with the details for those who have not gone through this EDL structure. But essentially what it means is that you have multiple capacitor within an electrode, and so the capacitance of an electrode that one measures is also equivalent of at least two, if not more. Okay, so all of those will essentially what they do is your capacitance actually of a unit cell becomes less than what is there individually in an EDL. Okay, now there is another type of capacitor. So these are called electrochemical capacitors. Okay, why they are called electrochemical capacitors? One, because now you have not only a solid, but you have an electrolyte solution, a solution having ions. This is normally called as electrolyte. Because this is a medium which allows flow of current, but not in using electrons. So current flows using ions, and when we have such kind of a situation where we have electron moving or electron conducting part of the structure and an ion conducting part of the structure, we call that those kind of devices as electrochemical. Okay, so EDLC therefore becomes electrochemical, although there is no electric to chemical conversion. This is EDLC still continues to store charge in electric form, but still categorized as electrochemical because we have both electrode and electrolyte in the device. There is another kind of electrochemical capacitor which is called a pseudo capacitor. So as the name suggests, it is pseudo. it is not really a capacitor, but it is called a pseudocapacitor because it also shows a behavior where the charge is proportional to the voltage of the device. Okay, so although it is not storing energy in electric form, but somehow because of some features, the charge stored shows a proportionality to the voltage. So as the charge is increased, the voltage of the device increases almost linearly, and as it is discharged, the voltage of the device also goes down or nearly linearly. So these characteristics are different from battery. For a battery, the discharge curve is a plateau or a slightly inclined plateau, which is to say that the charge supplied by a battery is very weak function of the voltage. So they remain more or less constant. Of course, no real device can provide a constant voltage, but they decline very slowly. On the other hand, all the capacitors, the voltage will decline very almost linearly with the amount of charge that it is supplying. So essentially what happens in pseudocapacitor is there is a reaction that occurs at the electrode, just like a battery. So therefore there is conversion from electric to chemical form and chemical to electric form during charge and discharge. And broadly, three kind of mechanisms have been identified for material that shows pseudocapacitance. One which is called as underpotential deposition. So this is essentially, for those who have not done electrochemistry, essentially what happens is there is a potential, a given value of thermodynamic potential at which any ion will reduce to metal. However, depending upon surface, sometimes if there are favorable surface interaction, then it is possible for ion to reduce below what is the thermodynamic value. So when that happens, then this deposition is called underpotential. Underpotential has to do with deposition or reduction occurring below the thermodynamic value. Okay. Again, not going into great details of it. Just for sake of completeness. The other one, an underpotential deposition, by the way, is not a very prominent mechanism which is used in pseudocapacitors. The more prominent one which are used is redox pseudocapacitance. So here what happens is there is a redox reaction that takes place at the surface. For those of you who are not aware what redox means reduction and oxidation. Oxidation means that the species gives out electron, and reduction means that the species accepts electrons. So for example, the reaction shown here, where ruthenium oxide with some hydroxide component takes some amount of protons and electron to convert to a different kind of ruthenium oxide. This is a reduction reaction in going from left to right because it is accepting electron. And if the reaction is reversed, it goes from right to left, then it becomes oxidation. So usually when charging is done, once we go from left to right, and when discharging is done, one goes from right to left. The same reaction is repeated in reverse direction, and therefore these processes are called as redox process. So when these processes occur on the surface of the electrode, then these processes are fast enough that they behave like a capacitor. Okay, battery has a slow response because then the reaction occurs inside the electrode, and when reaction occurs inside the electrode, then it is limited by the speed at which the reacting species can move into the porous solid structure. Okay? And so only difference here is that the reaction is confined to the surface. When that happens, because of some things that we are not putting here mathematically, it turns out that the charge stored, which is related to the reaction, amount of reaction has occurred, depends on the potential. The other mechanism, the third mechanism of pseudocapacitance is what is called as intercalation pseudocapacitance. So the intercalation, I believe all of you probably would know, is basically insertion of a gas species within a crystalline solid where the structure of the crystalline solid is not disturbed, is not broken. Okay, so all your lithium-ion battery essentially work on intercalation electrodes. Okay, and so it is also possible for some of these electrodes to show capacitance-like behavior if intercalation is confined only to the surface layers of the crystal. If it goes deep into the crystal, then it will start behaving like the battery. Okay, so there are therefore three types of mechanism: underpotential deposition, redox pseudocapacitance, intercalation pseudocapacitance. And the more commonly investigated electrodes are for redox pseudocapacitance and intercalation pseudocapacitance. Essentially, the amount of charge which is stored in a pseudocapacitive mechanism is much higher than electric double layer capacitance. Okay, so if we look at pseudocapacitor characteristic, energy stored in electrical form, specific capacitance is much higher than EDLC. So some estimates say that for every surface active uh, entity, an EDLC stores about 0.5 electron, while a pseudocapacitive electrode will store about 2.5 electrons, okay, of charge, electron units of charge. So therefore, the specific capacitance of the pseudocapacitive electrode is much higher than EDLC. However, what happens is that the operating voltage range is much smaller than EDLC. So there are some advantages with pseudocapacitance, but it also comes with its own flip side. Operating voltage window, if you recall the energy equation, energy stored is CV square. So if voltage window goes down, then it has much stronger effect on the net energy stored. On top of that, most of the pseudocapacitive material have low electronic conductivity. Okay? So that also affects the performance of the device in a very negative way, because the device then start to behave more like a resistor and less like a capacitor. Loading of the active material in the electrode is low. So for example, in this, all the electrodes which are made, the electrode is never a pure active material. It also requires some conductivity additions and some other additives for the electrode to be mechanically strong and other properties. And so therefore the net electrode, the amount of energy stored per unit weight of electrode becomes even lower if the proportion of active material which is holding the charge is lower. Okay, and because the response of formation of the electric double layer is very fast compared to the speed of reaction. Okay, so therefore the speed of once we say speed, essentially it means power density of pseudocapacitive electrode is also smaller than EDLC, and also the cycle life of EDLC is much higher than pseudocapacitor, and that again has to do with the fact that in a pseudocapacitor there are greater changes which happens to the electrode structure compared to EDLC, where there is essentially no change in the solid electrode part of the EDLC. Okay, now all of these electrochemical capacitors, they essentially contain two electrodes and an electrolyte. And electrolyte is one of the problematic part of the electrochemical capacitor. It is required, it's an essential part, but it also presents problem. And one of the biggest problem with the electrolyte is its conductivity. Its conductivity is much smaller than the electrode. So in an electrochemical device, the resistance of the device is primarily determined by the electrolyte. And so just briefly looking at the categories of electrolyte used, there are aqueous electrolyte, there are organic solvent based electrolyte and ionic liquid. And these are the three commonly used electrolyte. Sulfuric acid, 50% around, has highest conductivity, but again it is much smaller than the electrodes. Then we have 6 molar KOH solution around 500 millisiemens per centimeter. And sodium sulfate solution has much lower compared to the other two, but then it brings in advantage of operating window. So if you look at the operating window, which is the maximum voltage to which the capacitor can be charged, is around 1 volt for the first two aqueous electrolyte, while it is 1.4 volt for sodium sulfate solution because it suppresses the breakdown of water. Remember that if these solutions are based on water as solvent, then water starts to show splitting if the voltage at the electrode increases beyond 1.25. So that is somehow suppressed by sodium sulfate, so it can increase the voltage window. Therefore, people also use sodium sulfate solution in spite of having lower conductivity. Organic electrolytes, so acetonitrile with the TEABF4, which is tetraethyl ammonium borofluoride. So that is a salt and ACN is a solvent. The conductivity of organic solvent is even smaller and much smaller, very poor, because they are large molecule. Both the solvents are large molecule and the salts itself, the ions itself are large ions. So BF4, for example, will become the negative ion, and TEA will become the positive ion. Both of them are very large compared to a sodium ion or a proton. However, they provide much higher operating window, 2.5 to 3 volts. So from energy density point of view, mostly it is organic solvent which are used in supercapacitor. Of course, there is another one which is mostly in laboratory, which are called as ionic liquid. These are mostly imidazolial salts, and they have very poor conductivity, the current state of art 4. But they provide very high voltage window when we compare with other electrolyte, liquid electrolyte, so 4 to 4.5. Principally, they are still confined in research. Unless something can be done about their conductivity, they still will remain in the research labs. Of course, there's another problem associated with ionic liquid, which is their hazardous nature. They are much more environmentally hazardous than the other electrolytes. Now, what are the limitations that come because of electrolyte? So the limitations that come because of electrolyte is that the operating voltage window is basically determined by the electrolyte breakdown. So as we discussed in the previous slide, it is about 1 volt if one is using aqueous electrolyte. It becomes around 3 volt if organic electrolyte are used, but this is still much smaller than where the dielectric capacitors can go. Dielectric capacitor can go to up to tens of voltage, okay, up to the voltage where the in between dielectric does not break down. Electrolytic capacitor can go up to 100 of voltages because they have an alumina layer, aluminum oxide. So they can go up to hundreds of voltage. So compared to whatever gain is made in electrochemical capacitor because of higher capacitance, a lot of it is compromised because of the fact that the electrolyte will not allow more than 3 volts of operating voltage window. So therefore one loses out on this V square term, and it's a square term, so the effect is much higher. Okay. Now what is true about using this, or what the limitations further get compounded by the fact that most of the applications where we are looking for these use of electrochemical energy supply device actually require higher voltage than a single cell. Okay, so even some people have now done some addition to organic electrolyte to get the voltage window expanded to 3.5 close to 4, but that is still smaller than most of the application require from 9 to 64 volts. Okay, if we are talking about EV, requires 48 to 64 volt, and that has to do with the fact that most of these things run on DC current, and when you run on DC current, if the voltage is low, then the ohmic dissipation of energy is high. The ohmic dissipation, remember, is I square R. So if you have to supply same power, and the power supplied is VI, where I is current. So if you use a lower voltage, then a higher current is required, and as the current is increased, the ohmic dissipation of energy I square R will increase rapidly. Therefore, most of these devices will demand higher voltage depending upon how much is the current requirement. So how much is the power requirement. So electric vehicle which require higher power, higher energy will operate with system designed to work at 48 to 64 volts. Some of the more electronic circuits still require 9 volt. Most of our mobile batteries are, I believe, around 9 volts because all transistor logic and other things will work at voltages around 3, and some will run higher than that, so you require power supply which is higher than that. So what happens because of this requirement, if these electrochemical devices are to be used, then multiple cell needs to be connected in series to get to 9 volt or get to higher voltages. Of course, if you have to get to very high voltage, then some power electronics interface where voltage ramping up or voltage ramping down are also required to be put. So one is there is additional cost of putting those things, the power electronic interfaces. The second thing is that once these cells are connected in series, equivalent capacitance is going to reduce, and to manage the whole unit as a coherent energy supply unit, complex management system is required. Because even though they are manufactured in the same batch from the same manufacturer, different cells have some slight difference in their synthesis or makeup, and they also age differently, so they will discharge at different rate Okay, and when cells are connected in series and one is completely discharged while the others are charged, then the entire supply will not work very well, because the discharge cell will then behave like a ohmic contact, and therefore you cannot supply large current over over the supply. Okay, so therefore a complex management system is also required to ensure that cells are at similar state of charge, and when charging is done, it has to be ensured that all cells get fully charged, so that none of the cells are at a lower state of charge, because then during the discharge it is possible that these cells may become completely discharged. So these are complications that comes because of lower operating voltage window, which is a limitation brought in by electrolyte. The other limitation is that the increase this higher resistance of the electrolyte increases what is called as the equivalent series resistance of the capacitor. So this is all the resistance of the capacitor. Any component which are there in the capacitor, all of them, to an external circuit, what is the resistance that the capacitor presents. Okay, and this ESR, essentially in the equation I've written as R. So if you recall your school book, the rate at which the voltage will drop will depend upon the initial voltage times 1 minus e raised to the power minus t over RC. So essentially how fast the voltage goes down is essentially a measure of how fast the current is being supplied or power is being supplied. And so therefore that is determined by what is known as the RC time constant, or tau RC. Okay, so the response time of a capacitor depends on this parameter, the resistance, which is ESR, times the capacitance. Now for this electrochemical capacitor, capacitance is already high. We are not talking about microfarads, but we are talking in terms of hundreds of farads. So when we have a unit which has capacitance of 100 of farads, even a small increase in R, the product RC increases by a large amount. Okay, so a small increase in R makes capacitor response sluggish, and one of the attractive feature of capacitor is their speed of response, their power density. So if the power density goes down, then that is very detrimental to the attractiveness of the capacitor. Okay, so because of this higher ESR, response becomes sluggish, power density goes down. One of the things which also happens is speed of response going down. Also, in terms of looking at it in the frequency domain, means that beyond certain frequency, it does not remain behaving like a capacitor, but becomes like a resistor. Okay, so there is one which is DC operation, supplying energy, but then there is another application of capacitor, as we mentioned earlier, which is the filtering, and the filtering depends upon the frequency of the signal. So that frequency would require, so suppose we have power supply at 50 hertz, a rectification of 50 hertz will actually give you half sine waves at frequency of 100 hertz, and so one would require this device to remain capacitive at 100 hertz. Most of the electrochemical capacitors actually start behaving like resistor, because they cannot behave like a capacitor at higher frequency simply because the resistance is high, and so response time becomes slow. They cannot respond at such high frequency and essentially start behaving like a resistor. Just again, just to finish this part of the talk. So performance of these electrochemical devices, usually there are two parameters. One is the energy density and the other is power density. And why both are important is that one needs to have sufficient amount of energy to carry out the entire task which is required. Also at the same time, one requires power density. So the task also needs to be done at some reasonable speed. Otherwise, there is no meaning to do the task. To give an example, suppose you use an electrochemical device to power a two-wheeler or a car, and let's say that the electrochemical device has enough energy that it can run the car for 100 kilometers. Okay, so it looks attractive. It is in Indian condition, or let's say 300 kilometers. So it looks attractive everywhere on a single charge. But let's say that its power density is very poor, so car can only run at speed of 5 km per hour. Then nobody is going to use that car. Okay, there's no point using a car if you can travel only by 5 km per hour. So that's an example that shows that not only energy density but also power density. So both these combinations are a requirement. Even for mobile applications, the battery need to provide sufficient power for people playing games and other apps that are hungry on power. So not only you need the battery that can at least supply power for a day in case of mobile, but should also be able to run all of those power hungry apps in a good way. For example, Google Chrome is a power hungry app. So therefore, a device, electrochemical energy device or any device, one of the key parameters to look at is what is the energy density to power density thing. And of course, where we would like to have the device is on the right top corner, because that's the combination of high energy density and high power density. Okay. If you look at the different electrochemical energy storage device, this is where the conventional capacitors are. So they have very high power density but very poor energy density. So any application that requires little higher energy, they cannot be used. Okay. Supercapacitor are somewhere here. The energy densities are at least an order of magnitude higher. It is in the range of 5 to 10 watt hour per kg. Power density, of course, here it is shown much more in favor of supercapacitor, but its power density is just about the lower end of the conventional capacitor. And then we have batteries which have higher energy density, so they are higher, but their power density is very poor. Lithium-ion batteries are somewhere here. Okay? And then fuel cell, which have even higher power energy density, but they have poor power density. And since we are here, uh, just to add to this discussion, uh, these electrochemical energy supply devices, for example, battery. So if you recall Daniel cell, they were all made in 1780s. Okay, while the IC engine came in late 1880s. Okay, I'm talking about the internal combustion. The external, well, of course, the steam engine was there for a long time, but ICE came much later. However, if you see, the batteries have continued to remain powering only the very small power or energy required applications, while IC internal combustion engine have moved on to power electric vehicle. And one of the reason is that on this graph, if one has to plot a gasoline engine, it will come right here where the goal is. Okay, so why IC engine got popularity or got the market, even though their development was late, was because they hit this wagon plot on the right top corner, while the electrochemical devices are all are far from here, and that's one of the reasons why various electrochemical devices are important in the sense that they, depending upon the energy and power density, they can be good match for certain kind of application. So there are certain kind of application where supercapacitor is a good match and battery cannot do that job. And there are certain application where battery is a good match and supercapacitor cannot do. So therefore all electrochemical devices, they have their own window of operation in terms of application for which they are suitable. And eventually one of these devices will probably reach somewhere here, and if it so happens that only one of them reaches, then that will start dominating. But in the time, till the time we are far below IC engine place in the Ragon plot, each device will have its own merits. Now, again, just to conclude this slide, the conventional batteries, because of higher energies, are actually good for continuous power for a long time. So power is not very high, but you need to supply it for a long time. On the other hand, supercapacitors are good for frequent power supply, which is a pulse power, but not for long time power supply. Now, again, since we are here, the supercapacitors have very high cycle life. It is in 100,000 to million for conventional capacitor, while batteries have low, comparatively much lower cycle life. So lithium-ion batteries, for example, used in Tesla car, a cycle life of about 3,000, which works out to about 8 years of life in the car. Okay, one of the reasons for this is that the cost of the car is high and one has to think about other mechanism of battery swapping or other things. So that's the kind of differences. Batteries 3,000 for lithium ion, for lead acid battery is even lower. So the batteries that we have in our inverter at home, it's only 200, 300 cycles. On the other hand, capacitors are for very frequent charge discharge. They can go up to 100,000 is on the lower side. Even for supercapacitor, they can go up to 300,000, 500,000 cycles. Okay, now one of the final slides, I believe, in this part of the talk is about how there are other mechanisms by which the energy density of capacitors is being tried to improve, which is what is called as hybrid capacitor. And the way it is done is to improve the voltage window. So here it is an EDLC device schematically with the curve below showing how the capacitance, how the voltage changes as the charge goes down. So the left, the charge goes to zero, voltage also goes to zero, and as we increase the charge, then the voltage goes high. Okay. For a redox reaction type, which is more battery or pseudo capacitor kind of device, the voltage remains constant for most of the charge supply and only starts to change or fall down or go up if it is a negative voltage towards zero, only towards the very end of the charge supply. So what one can do is, if we can combine a cell, remember that an electrochemical device requires two electrodes. So how about one electrode being EDLC, the other electrode being a pseudocapacitor or a battery-like electrode? When that happens, then the voltage of the device will not fall very sharply, because though the voltage of one of the electrode is falling, the voltage of other electrode will not fall. And when that happens, then the voltage window will continue to remain wide because one of it is not changing. So this is one way where the energy density of capacitors, supercapacitors, is improved by mixing electrodes with different mechanism of charge. There is also a bigger category of this, which is called as asymmetric capacitor, where both the electrode could be EDLC. So both may be showing a linear declining curve, but in different voltage ranges. So the net difference between the two electrodes, which is the cell voltage, still remains a wider window than a symmetric capacitor. Okay, now in the second part of this or B part of the first part of the talk, what we will do primarily is to look at some of the electrode material, because the electrode is the prime determinant of the energy. And so if you look, these devices are closed system. So whatever material one puts in electrode, that is the energy. There is no energy that is flowing in. It's a closed device, no material flows in. And electrode is a complex structure consisting of active material, conductivity, enhancer, and binder. So the net energy of the electrode per unit weight, the weight is not just active material but other additives which are put. Therefore, it is important that the active material carry as high energy or provide as high capacitance as possible. So if you look at EDLC, again, in this talk, this is just a glimpse of things. This is not a comprehensive review, and I'll just rush through it. So capacitance is proportional to surface area and requires high electronic conductivity for fast response. And on both of these, apart from this, the material should also be resistance or chemically resistive to electrolyte environment. And carbon actually provides that all of these properties. It is enabled to different morphologies, porous morphologies that provide higher surface area. If one goes to graphitic form, that has good conductivity, has good chemical stability, abundant, cheap, and non-toxic. So EDLC electrode, if you look at in literature, most of them are carbon-based. And carbons, it goes in different forms. So you can have it in zero dimensional, which is the fullerenes. You can have nanotubes, which are one-dimensional. You can have graphite or graphene, which is 2D again. And one can have then graphite, which is 3D. So all these forms of carbon is possible. And 1D and 2D form provides much higher specific surface area. And then, of course, even in 3D form, if carbon is it is very good material to be made into different porous morphologies. And these porous morphologies can provide very high surface area. So, for example, activated carbon, people have reported up to 1500 meters square per gram, which is very high surface area. And such activated carbon can provide a capacitance of around 200 farads per gram in aqueous electrolyte and 100 farads per gram in organic electrolyte. this is just a glimpse of what kind of research goes on. So earlier the belief was, or traditional view based on the equation was, that if you use porous material and reduce the surface, the size of the pore, the idea is to reduce size of the pore because then more surface area gets generated because one can pack in more number of pores in the same material. However, what happens is the ion diameter is a certain value, and when the pore size becomes less than the ion hydrated ion diameter, then the ion will not be able to enter a pore. And so if that happens, then the smaller pores will not contribute to capacitance, and therefore the capacitance will go down. So as the average surface size goes down, the capacitance will go down, and there were studies which actually showed that. However, then there came newer studies that if you go down to much below that range, then actually capacitance starts to increase, and people have researched why this happens. And one of the ways to explain that is what happens at very low pore size is that these hydration layer goes away. So there is a solvent molecule layer around each ion in a solution, and that layer goes away. Therefore, the ion size becomes smaller and it can enter the pore. And when that happens, then you get a sharp increase in the capacitance. So this is just to explain that there are a lot of other unexplored things which still exist, although it's a pretty mature area, but still there are possibilities of improvement in the performance of carbon-based EDLC electrode. For pseudocapacitive material, the first noticeable material of extremely high capacitance was the ruthenium oxide. It was hydrated form of it, something that we saw earlier. And this is one of the rare pseudocapacitive material that also has good conductivity and therefore shows very good rate capability, shows very high specific capacitance of 1400 farads per gram. However, this is not a commercial, could not be commercialized because of very high cost of ruthenium. Okay, so this was the first major pseudocapacitive material that brought in this thought into the domain that pseudocapacitance can be used as a possible electrochemical capacitive device. However, ruthenium, though it showed the path, it cannot be commercialized simply because of the cost of ruthenium. Other materials which are used are mostly transition metal oxide. So transition metal based, it's not just oxide, but different transition metal based compounds. And most of these compounds have poor conductivity, most of them. At least the oxides have poor electronic conductivity, and that's one of the drawbacks of pseudocapacitive material. So if you look at different mechanisms, we'll only look at the redox pseudocapacitance and the intercalation pseudocapacitance. So most are transition metal based materials. So there are transition metal oxide which are of spinal or mixed spinal structure. There are transition metal sulfides which are being explored. There are transition metal nitrides. There are some chemical formulae for them. There is layered double hydroxide, another material which is different from oxides and of course contains hydroxide in its structure. And then there are conducting polymers. So some of the more interesting materials reported in literature are given here. The idea is not to bombard you with all of it. Of course, it requires many hours to discuss all of these materials, so simply not possible in this talk. If you look at redox pseudocapacitor, sorry, there's a mistake here. This is intercalation pseudocapacitive material, not redox. Then you have transition metal oxide. You have lithium and sodium transition metal sulfides. So again, so formulas are not here. These should be sulfide. Then there are transition metal sulfides, and then transition metal carbides, some things which are also called as mexenes. So these are materials which are used as in intercalation pseudocapacitor. So please ignore the title. It is not redox. It is intercalation pseudocapacitive materials. Okay. The final part of the first part of the talk is on galvano. So how to characterize a capacitor. So there are two different techniques which are used, which is the GCD, the galvanostatic charge discharge, which is charging at constant current followed by discharging at constant current. So this is how an ideal capacitor will behave because it shows the linear behavior. So during charge, the potential will rise. And when the discharge is done, the potential will go down. So this is for an ideal capacitor, but no capacitor is an ideal capacitor. There is always a resistor or resistive element to it. So a good real capacitor will show a charge behavior which is still linear, but then there is a drop as soon as there is a switch from charge to discharge, and then again linear. Again, this is an ideal capacitor, but with resistive component. The other characterization technique which is commonly used is cyclic voltammetry, where one applies a constant ramp of potential and then track back the path. Essentially, that is what cyclic voltammetry is, and then measure the current. Okay, so this is how the CV for different capacitor will look like. For an ideal behavior, this is EDL, this is CV for an EDLC, this is for a pseudo-capacitive electrode. This is, of course, the charge discharge, the Galvan GCD curve. For other types of thing, the intercalation pseudo-capacitive, you will get something which is like a capacitor, but then there is something which is like battery. For intercalation, you have a different kind of shape. So people have studied and found that there are different kinds of characteristic feature that these devices will give, and this is used to identify what is the kind of energy storage mechanism in an electrode that shows capacitor-like behavior. Okay, so with this we'll end the first part of the talk, and maybe in the remaining 20 minutes or so, 20 or 30 minutes, we'll just look at a glimpse of some of the work that we have been doing in past few years in our lab. And as I said, that we will be looking at two works in different domain. One of the work is to look at how to improve the energy density of EDLC electrode. So that's focused on the energy density. The other part of the work where the glimpse is shown is to show how to improve the rate or response time of the capacitors good enough such that it can also be used for filtering application. So there is, so the first part of this, first glimpse is basically titled as vertically oriented graphene nanoflakes capacitor electrode. Okay, so if you look at carbon-based EDLC electrode, we have active carbon plus binder plus carbon black, which is conductivity enhancer on a current collector. So this is what an electrode looks like. Okay, and usually the composition is that the activated carbon is about 30% by weight. Okay, so an activated carbon can provide an energy density based on its capacitance of about 100 farads per gram, can provide an energy density of 20 watt-hour per kg, provided that the thickness of the electrode is 200 micron. But since it is only 38%, if we actually calculate the energy per unit weight of the electrode, remember in the device the entire electrode is going, not just AC, so all the weight of the electrode has to be accounted for. And when that is done, then the energy density and specific energy of the device reduces to about 5 watt-hour per kg. Okay, this is what is shown in the graph here. So if you only have carbon, okay, then if you have carbon plus there is a current collector, and then carbon and collector, but the carbon is of a smaller thickness. Okay, so what is shown here is these are the values which you will find reported in research papers. This is only the active material values. This is Ragon plot again, presented flip side. So power density is on the y-axis and energy density is on the x-axis. So these are the values which are reported in literature. So you'll see 20 watt-hour kg, 30 watt-hour kg. Those are mostly for the active material. However, if you come with the active material which has to be loaded onto the current collector, then one gets to value which are here. Okay, and if the carbon loading is much smaller, then the collector remains the same. So therefore, the weight of the collector current collector becomes much higher fraction than the active material. Then the value will come down to what is here on the orange curve. So there is a lot of difference between the energy density of active material to energy density of the real electrode based on how large the loading of the active material or the thickness of the active electrode is. Okay. The other way to construct electrode is to have a freestanding carbon electrode. Okay. People have reported graphene aerogels, papers, carbon paper. These have excellent conductivity. So why a current collector is used is because this activated carbon is a porous material and uses porous material has even more reduced conductivity, because then there are paths for electron conduction becomes less because much of the space is occupied by the pores, and therefore current collector is required, otherwise there is lot of contact resistance. However, if one uses these materials like graphene aerogels, papers, they themselves have excellent conductivity, therefore current collector is not required. Okay. However, what happens is even in these kinds of materials, so these are freestanding carbon electrode, not a composition which is like this. Okay. Here, mostly the values are reported for small loading again. Okay. And again, the same thing, that if you have carbon material of certain weight, which is a device with a 2 micrometer film, then you reported values are here, but that is too thin to provide sufficient mechanical strength. Okay, a device with 120 micrometer film may be having a sufficient enough strength, but usually one would be looking at something which has a carbon electrode of the specific weight of 8 to 10 milligrams per centimeter square. And again, when one goes there, the energy value decreases. However, this still provides better avenues for increasing the energy density compared to electrodes, where the composition is active material, binder, conductivity, enhancer, current collector. This is, by the way, the preferred and mostly available composition for commercial capacitor. The one on the right hand side is mostly in the laboratory. So one of the things which have been explored here is to construct an electrode where one has vertically oriented graphene nanoflakes. So you have a conductive substrate and then somehow arrange graphene flakes which are vertically oriented so that they provide higher area. They should not be horizontally oriented as shown here, because if that happens, then the lot of surface area of graphene is actually hidden in the stacking and is not available to electrolyte. So people have done this using CVD application, but then there is another part which is being done, which is to exfoliate the graphite. So your conductive base remains graphite, and then some of the layers of the graphite are kind of peeled partially. So they are peeled partially and moved up. Okay? And if that is done, then they become vertically oriented graphene flakes. So this is something that we tried at our laboratory here. Here is some of the characterization just in brief. So these are SEM micrograph of the graphite electrode. So this is pristine HOPG, highly oriented pyrolytic graphite, synthetic graphite. This is the top view. And on the right hand side is a cross view where you can see the layers are so tightly stacked that one cannot make out the layers. Okay. When we did exfoliation, partial exfoliation, the top surface, so the bottom two figures, the left hand side is the top surface of the same material. So what is there on the top here, this is what happens after exfoliation, and one can see these graphene nanoflakes which have come out of the surface in vertical orientation. And during the process, not only these flakes come out from the top surface, but this is what happens in a cross view. You see that the layer also get partially delaminated, and there is a lot of open spaces which are created between the graphene layers, which are not visible in the previous before exfoliation of pristine electrode. So both of these increase the surface area and therefore improve the capacitance. These are some material characterization, again not spending time, so we looked at what happens to their crystal structure defects using Raman spectroscopy. And when we do this technique, some oxidation takes place. So what are the oxidation, whether we get CO bonds, COC, or carboxylic acid bonds. And these are actually both detrimental in performance and also aid in performance. They are detrimental in the sense that whenever one gets an oxygenated surface or edge in the graphene, the electronic conductivity goes down. But the positive side is these can then lead to oxidation and reduction on the surface, these oxygenated groups, so therefore they can provide pseudo-capacitive character. Okay, so different synthesis route that we followed. So we followed two synthesis route. One is pre-intercalation of electrolyte and then exfoliation. The other one was direct exfoliation. This was done in ammonium sulfate solution at 90 milliampere per centimeter square for 1200 seconds. And what we see is that, excuse me, for the pre-intercalated route, the aerial capacitance that we obtained was about 25% higher than the direct exfoliation route. So we continue to use the pre-intercalation route to synthesis. And then what we did was that we looked at the effect of the counter ions. So we looked at different sulfate salts as electrolyte for exfoliation, all solutions having concentration of 0.1 molar. And we saw that the best results were obtained in sulfuric acid solution. Okay. Now, one of the things with sulfuric acid is that when you use sulfuric acid, the pH is different from other salt. Okay, so we manage the pH of these salts also. And in order to do that, we conducted studies at different pH. And what we found was that the pH of 1 molar sulfuric acid, which is 0, gave better results. Of course, 0.1 molar sulfuric acid also gave nearly the same results. With this, what we did was, therefore, did this partial exfoliation in 0.1 molar sulfuric acid, but looked at time of exfoliation, and we found that 1200 gave better results. Of course, with the current density we were using, we could not go beyond 1200 seconds, because after that, enough of the material has detached from the electrode that it did not have the required mechanical strength. These are some of the characterization of the best prepared electrode. So here is a galvanostatic charge discharge curve that we showed earlier. So in an ideal capacitor, which is never found, you will have a triangle, a straight line going up and a straight line going down. In a real device, you will have a slightly curved, but still more or less linear. So here is the performance. So these are at different current density, 1 milliampere per centimeter square to 10 milliampere per centimeter square. And what kind of charge discharge curve it gives. Based on this charge discharge curve, one can calculate the aerial capacitance, that is capacitance per unit geometric area, in 1200 seconds, gave very good results of about 0.75 millifarads per centimeter square. This is the same characterization for a symmetric capacitor made out of those electrodes. So we took two of such electrodes, combined them together, and put sodium sulfate as an electrolyte, so aqueous solution, and this is the curve that you get. Now in this curve, for a capacitor, because now there is still thicker volume of electrolyte, you will start seeing the IR drop that we were talking about. So resistance becomes, ESR becomes a noticeable component here. We just look compared with literature where our capacitor is in terms of volumetric capacitance. These are some of the best values reported in literature. The red balls here is the performance of our capacitor, and of course it is comparable with literature. Here what we had done was we combined 3 capacitors in series so that the voltage becomes high enough to light an LED. So this is a photograph showing an LED here which was powered by the capacitor. Okay, so just to summarize, it was shown that the partial exfoliation can provide self-standing EDLC electrodes. Electrolyte pH affects the degree of expansion and exfoliation rate, and therefore played an important role in the density of graphene nanofilms that one can get. Sulfuric acid amongst the all sulfate salts. So remember, this is not an absolute statement. We did not try all the salts. Amongst the sulfate-based salts, sulfuric acid turned out to be the best electrolyte. And of course, the electrode with exfoliation time of 1200 seconds shows capacitance of up to 1.56 farads per centimeter cube at 2 milliampere per centimeter square current density. Okay. So with this, we move to the final part, which is the a capacitor, which so it's a supercapacitor, which still has fast enough response that it shows capacitive behavior even at higher frequencies. Okay. So this is again something that we worked in our lab over past 4-5 years. So essentially what is AC filtering? So of course all of this data is based on the the supply frequency which is in the Western country. So we work on 50 hertz, US works on 60 hertz. Okay. So sine wave, this is like the power supply, which completes one wave in 60. So 60 such waves are completed in 1 second. That is what is meant by 60 hertz. So when you rectify it, now half of the wave becomes the full wave. So therefore frequency doubles and becomes 120 hertz. Okay. So if this is how a schematic of a full wave rectifier. So their diodes are in this way, and this is how a sinusoidal signal will get converted, will get rectified. However, if you are trying to use this as a DC power supply, then there is a lot of fluctuations, right? And these fluctuations are not good enough for the is not good for the device. So therefore, what is done is in this filtering circuit, a capacitor is put. So what happens is the capacitor gets charged during the rising part of the cycle, and when the supply cycle is going down, the voltage doesn't go down because the capacitor then starts to supply, and therefore this curve will come down slowly, and it will depend upon how the capacitor is discharging. So if you can provide a good enough capacitor, then this downward movement can be arrested or controlled or can be reduced to a very small degree, and this is what is called as filtering. So you will start getting a flat curve as the output. Okay, so this is what is done in all filtering circuit, and the aluminum electrolytic capacitors are used. Okay, as we were mentioning in the first part of the talk, so they remain the bulkiest component simply because these capacitors, the amount of capacitance that they have is about 20 to 40 microfarads per centimeter square. Okay. On the other hand, all the electrochemical capacitors that we talked about, carbon electrodes with high capacitance, they cannot respond as capacitor for signal beyond 5 hertz. So as soon as you go to 10 hertz, there is no capacitive behavior which is shown by them. They only show a behavior like a resistance, and that has to do with higher ESR. Okay, so therefore there is a gap which exists, wherein if it is possible to create supercapacitor with low ESR such that they have frequency response at least up to 120 frequency is one benchmark, and up to 1000 hertz is another benchmark, therefore kilohertz frequency response capacitor, then there is a lot of market, because all of these AC-DC converter or filter part of those will become very small, and when they become small, there is a lot of market for them. Okay. So people started looking at using electrochemical capacitor for it, and what they found was that porous electrolyte resistance increases because the pores are narrow and also they are tortuous. So if one can go with wide straight pore morphology, then it is possible to get a phase angle of -90. By the way, capacitive behavior is -90-degree phase angle. Okay, so as soon as you start going away from -90 degree in an impedance plot, then you move away from the capacitor. So if you look at the state of art in research paper on EDLC, which are used for kilohertz supercapacitor, kilohertz frequency response, then these are all graphene based. Okay, they're all graphene based. This is the aerial capacitance as 120 hertz. That becomes a characteristic feature now. E marker, and these are the phase angles. Closer to -90, the better it is capacitive behavior, and corresponding RC time constants. What is the resistance? So if you see, all of them are all carbon and mostly graphene based, which means that their capacitive mechanism is EDLC, electric double layer capacitor. And as a result, because you have to maintain straight pore, there is not much increase in the surface area which is possible, and that results in a limitation on them also. Okay, so there is a possibility that if one can make pseudo-capacitive electrode with higher frequency response, then because pseudo-capacitance is not limited by the surface area that much, it depends upon what kind of redox reaction is taking place, then it is possible to increase the capacitance. Okay, so these are all 194. This carbon black which is showing 800 is out of place, and that has to do with multiple layers being there. Okay, so the amount of material being put there is high. Similarly for this 3550. So don't consider those outliers. There are some other things that goes in. Okay, so what we did in our lab was to look at titanium-based pseudocapacitor. So this is TiO2. So essentially, we start with a titanium metal foil, do a anodization of it to generate pores on it, and these pores are titanium oxide. So essentially, what happens is when we anodize it, then the pores are formed of the titanium oxide, and this is well known. This is used for preparing some microfiltration membrane for gas for separation. But what we did was that we tried to do some modification here so that these smooth pore walls are made into a rough pore walls. And when you make rough pore walls, then the area of the pores will increase, and therefore it is possible to have more capacitance in the same geometric area. So that is in schematic what we tried to do in preparing this pseudocapacitive electrode. Okay, so there are different voltages at which it was oxidized for 50 minutes in 0.25 molar ammonium fluoride solution. So this is FESM image. So if you see here, you can see more or less regular pores, cylindrical pores of titanium formed over titanium. And if we do it for higher voltage, so this is done at 20. Here 20 EA, for example, is electrode name. 20 is the voltage at which it was done. So if you do at higher voltage, as you can see, while here there is not that hint of roughness, the hint of roughness here becomes more, and that is because cluster of nanoparticles are now starting forming over what was earlier a more or less smooth pore wall. If you go to 50 volts, then you can see that these are all dominated by these clusters, nanoparticle clusters, and these are so you don't see much of the tube geometry here, but all of these lumen that you see is remnant of these tubes. So if we go to higher voltage, first the tubes are formed, then these nanoparticle clusters are formed. So you still get lumen which are more or less straight, but now you get a rough boundaries of these lumen and therefore more surface area. And of course, what we did, one of the features is that these needs to be reduced in order to improve the conductivity. So once you form titanium oxide, it has lower conductivity. So we found that if we electrochemically reduce it, the conductivity improves. And still, so this EAR means it is reduced, still has lumen, still has rough or cluster of nanoparticles, titanium nanoparticles around those lumens. So therefore, high surface area, straight pores structure. Then again some characterization. So XRD to see titanium is found, what other phases are found. And then some EDX to see what is the oxygen here, and then of course do XPS, because that will give a much better understanding of whether we have oxygenation here. And one of the things with titanium oxide is if the oxygen to titanium ratio is reduced, then the conductivity increases. The defects, these are known as defects. So if these are oxygen deficiency defects, then it increases the electronic conductivity. So this is what is shown here. The O to Ti ratio was 2.75 in the unreduced anodized electrode, and when it is reduced, it reduces to 2.59, which is a substantial reduction. These are then the electrical characterization. So the left-hand curve here shows the phase angle for electrodes anodized at different voltage, and the right-hand side shows the capacitance calculated from the Nyquist plot here shown here. And so if you see that there is high capacitance as the frequency is low, so between 1 and 5 you can see high capacitance. It reduces as the frequency goes down, but there is sufficient capacitive behavior still, which is seen with phase angle more than -75. And of course, it continues to decrease as the frequency is increased. Okay, so we selected the electrode that shows the best performance in terms of high phase angle. High phase angle means closer to -90, and higher value of capacitance at 120. So this dotted vertical line is the frequency 120 Hertz. Same here. Then we looked at the effect of synthesis parameters. So reduction potential, different reduction potential of -1 and -1.5 volts. And as you can see, At 1 volt, there is certain performance, 1.5 volt is much better, and when we go to minus 2 volts reduction, then it again deteriorated. So we selected 1.5 volts. Capacitance is also shown. So one left-hand side is the phase angle to show it is still capacitive, and the right-hand side curve shows the aerial capacitance. Then we looked at what is the effect of reduction time at minus 1.4 reduction, and these are for 3 minutes, 5 minutes, 10 minutes, 20 and 40 minutes of reduction time. There is little difference which one can see from this graph, but there is some noticeable difference. We are not going into details for the sake of time. So once we get this electrode, what we did was we looked at whether this electrode can perform any filtration. And when I say filter, this is signal filtering. Okay. So we made a full wave rectifier. This capacitor was the capacitor made out of the electrode, that titanium electrode, and the curve which is here, the green curve is the input signal. The orange curve here is the rectified signal without the capacitor in the circuits. As you can see, the negative part of the wave is filtered by the diodes here, but it is all half sine waves. Okay. And then what we did was we brought in capacitor. Of course, there is a load resistor which is not shown here. And this is what happens to the signal. Okay, so the signal which was half sine wave now becomes almost a smooth line. Okay, and this is done for signals at different frequencies. So this is done, I believe we have not written here, for about 120 hertz. This is for as high as 50,000 hertz. Okay, so we can go to this signal. This capacitor can beautifully filter the signal to frequencies as high as 50,000 hertz. Now, why such a high frequency? So if you look, people are also looking for very high frequency filtering. So for example, the best values which are reported is at 20 kilohertz, a capacitance of 67 microfarads per centimeter square, or at 80 kilohertz, a capacitance of 67 microfarads per centimeter. These are all carbon-based electrode. Okay, acid treated poly 3,4-ethylene dioxythiophene. So these are all polymer which are then partially reduced to carbon. For our capacitor, so there is something called as SRF, which is the maximum frequency at which the capacitive behavior is shown. After that, the inductive behavior comes in. So that's a minimum in the curve. Of course, it is not shown here, it does not become that visible. For our capacitor, the SRF was 60 kilohertz. So therefore, we could even filter the signal at 50 kilohertz. So at 60 kilohertz, our aerial capacitance was 190 microfarads per centimeter square, which compares very well with the best values reported in literature. Okay, so this is a glimpse of the fact that pseudo-capacitance, which were generally considered to be always going to be low performing compared to EDLs in terms of speed, it is possible to engineer them, both their nanostructuring by having nanoparticles clustered in a straight lumen, around straight lumen, and also some defect engineering to introduce oxygen vacancies and thereby increase the conductivity to still get a fast response pseudocapacitor. Once you get pseudocapacitor, then the capacitance is always going to be higher than EDLC electrodes. So to summarize this study, we showed that it is possible to have kilohertz frequency response capacitor, and we showed it using titanium. Of course, electrochemical reduction of titanium improves electrical conductivity is something that I did not include in this talk. The maximum aerial capacitance was about 212 microfarads per centimeter square. Compare this with around 30 to 40 for aluminum electrolyte capacitor, which are presently used in all commercial filtering circuit. It's about 6-7 times. So if this was to be used, then the size of the capacitance can go down maybe by 4 or 5 times. And the phase angle was minus 81.6 at 120 hertz. So that's closer to minus 90 degree. The resistance time constant or the RC time constant is around 0.2 milliseconds, which is comparable with the best values reported in literature, and the SRF or the self-resonant frequency of 60 kilohertz is much more than those reported in the literature. So I'll stop my talk here. We are acknowledging all of this. So although I get to come here, talk and show that this is what we have done, but this work is not possible if it is not supported in different ways. So for example, IIT Delhi for providing all the facilities that we use, the MES division of DST for funding some part of this work, the characterization facilities at IIT Delhi, the nano research facility and the central research facilities. And of course, although I get to speak here, but most of these experiments are done by the students. So some of the students who primarily did the work that I showed towards the later half of the talk, Rupesh, Afghan, were both PhD students, and Deepak who did MTech here. So it's all their hard work that I'm presenting here. So with thanks to them, I thank you all for patient hearing, and I'll be happy to answer if you have any questions. So I'll stop here. I think it's around 10:50, so we have around 20 minutes for discussion if there are any questions.
Thank you, Professor Shukla, for such a wonderful talk and a very informative one. So now the session is open for the discussion or the questions, queries, if any, from the participant side. Yes, please.
Yeah, good morning, sir.
Yeah.
I am Anupama from NIT Rourkela Research Scholar. So I want to ask, sir, you have shown in one slide about this activated carbon plus carbon black plus binder, and you have shown in power density and energy density graph. So can you just explain one more time, sir, that?
Let me go to that slide.
Yes, sir. Okay, sir. Yes, sir. This one, sir.
Okay, so what we are saying here is just to build the background to the study. So what happens in most of the commercial or one of the major technology, remember supercapacitor is a technology which is still in development. Although there are commercial supercapacitors, Maxwell in US is one of the more prominent company. And what happens is activated carbon based electrode are the state-of-art electrodes if we go to practical devices which are used in applications, right? So what happens there is one uses activated carbon. What is activated carbon is it's essentially porous carbon with some functionalities, okay? And so the carbon, if it is not in perfect graphitic form, has a lower electronic conductivity that gets compounded by the fact that these particles are porous, so there are even lesser conducting paths. If you have a bulk solid or a dense solid, then there are a lot more connections between different atoms and molecules. Okay, and so in a porous carbon, the conductivity, electronic conductivity is less than a similar form of carbon having a non-porous structure. Okay, so therefore, activated carbon, though provide very high surface area, has a poor conductivity, poor electronic conductivity, and usually it will come in form of powder. Okay, so if you have to make an electrode, there are two things required. One, you have to make a mechanical structure, so there has to be a binder which will connect and hold these particles together. Okay, the binder are usually they are mostly polymeric in origin, so they do not provide any conductivity. So activated carbon plus binder itself is not something that will work as a good electrode. You require conductivity enhancer, so there is carbon black which is added. Now, even with all of this is a particulate structure somehow fixed together. Okay, so if you have to connect to a circuit, you just simply cannot connect. Suppose you have an electrode with a geometric area of 10 centimeters square, and you just connect it with a copper wire. Okay, it will connect at one point. Okay, let's say it connects with 10,000 particles. The other particles, the current has to flow through long paths, and therefore the longer the path, the more the resistance. So therefore a current collector is always used. This current collector is usually copper or aluminum. So this current collector is tightly pressed with the electrode, and therefore all the particles have a direct contact with the current collector or most of the particles. And then your external circuit copper wire can connect to the current collector. Okay, so that way the contact resistance is minimized. So what is shown in this graph is that, for example, here where my cursor is, these are the maximum reported values. But what are these values? As they show here the color, this is for the carbon, which is to say here activated carbon. Okay. Then if you get to carbon material with 10 milligram per centimeter square, your energy density is and power density both are reducing. Okay, because you have to keep adding these materials now to make electrode. Okay. And if you make a device with 10 milligram per centimeter square, so this is, let's say, for the material with all this combination which can get to an electrode, now you make a device. The device is 2 electrodes, plus you have electrolyte, plus you will have a separator so that they don't short circuit. Right? So the device power density and energy density is even lower. So there is a lot of gap between what is the maximum reported value that people report for their material to what the actual device that will be made out of those materials. And then there are two things. One is device where there is 1 milligram of carbon per centimeter square. So this per centimeter of electrode has carbon and current collector. And when we say carbon, it has activated carbon binder and CB. Okay, so the oranges curve is for 1 milligram loading and the blue curve is for 10 milligram.
Yes, sir. That means, sir, the starting material what we have taken, that value we are calculating. Then after making the device, how those values are decreasing. That thing we have shown here in this graph.
That thing is shown here because see to give you a background, what happens is many of the morphologies are being discussed for getting higher electrode capacitance, higher areal or specific capacitance of the active material. But this paper actually discussed the fact that some of these morphologies may not be very good when you go to device because it is not possible to load a lot of material in the device. For example, the one that I showed, graphene nanoflakes, right? So when you have graphene nanoflakes, although it looks very good, but it also suffers from disadvantage that you cannot, the distance between the two electrodes cannot be reduced very much. You cannot hard press them because then the vertical graphene nanoflakes will get compressed and you will get into a stacking kind of structure of the graphene. So therefore although not part of this graph, this is only showing that you just don't just look at the material specific capacitance. Look at how that material can be packed into device, and when you pack into device, can you load 10 milligram per centimeter square? If you can only load 1 milligram per centimeter square, then you go much lower. So that is what is being tried to say here, and based on that, there is an argument that it is better to probably look at self-standing electrode which does not require current collector. So that's the message from this.
Yes, sir. Sir, one more doubt. What is the minimum electrical conductivity should be there in the carbon black material to add to increase the, sir, conductivity? If
So,
our activity.
so I don't remember the electric conductivity value of carbon black, but essentially to give you an idea, the ESR of these devices, so full cell, usually comes to about 0.0104, 01 to 06 ohms.
Okay, sir.
Per centimeter square. So, or even in fact for complete devices, it would be like 0.04 ohm. So that is for the device counting the electrolyte. So the carbon back conductivity, you will have to maybe back calculate from that.
Okay, sir. If something we are getting, sir, activated carbon around 1 ms per second electrical conductivity, is that, sir, is that is enough for with having porosity also? So is that we can take it is having good properties, sir?
So see, just here I cannot say because these are numbers to be crunched. First thing is 1 milli Siemens per centimeter is what you mean, not second. Uh, the point is that you have to balance this with how big is the surface area because remember that the lower the conductivity, the lesser will be the weight here. The only thing you have to look is eventually when you make an electrode, what kind of energy density it gets. So for example, if your material activated carbon can provide 30 watt hour per kg, okay, just for argument's sake, then maybe you can be good with not 38% but 25% and still get to 5 whatever per kg by increasing carbon black. So lower conductivity of activated carbon is compensated by adding more carbon black. So those are the things that you will have to weigh in. There is no one answer to this. If it is too, so it is a combination of what is electrical conductivity plus what is the specific capacitance that it is providing, and whether then the amount of loading that you provide actually provides an electrode or a device with. So current state of art for commercial supercapacitor is 5 to 7 watt hour per kg. If you can build something which is 10, 15, then it doesn't matter whether the conductivity of carbon was low. Of course, you can always improve upon it by maybe reducing it, but the whole argument is that you cannot just look at one variable. You have to look at both the conductivity as well as capacitance, and then find the best combination.
Yes, sir. Thank you very much, sir. Thank you.
Any other question, please? Any other question, please? Professor Shukla, that ESR measurements is an important characterization for the electrochemical capacitor.
Yeah.
We slightly discuss it that why it is so important.
Yeah. So as I said that the one of the key thing about supercapacitor, if you look at the Regone plot here, supercapacitor, as we discussed, they are good and they will find application only if their power density remains high. Okay? Because energy density, the batteries are already there. So either we go here, we move supercapacitor to the top left, or we go to the top. Top right is difficult. What happens is every time one tries to improve the energy density of the capacitor, the power density comes down, as we looked at in the second part of glimpse of my work. So essentially, if you go somewhere here, there may be some application that one may find, but you will lose out on application where capacitors are there primarily to provide the required power density. Okay. So, and what the power density depends on? It depends on the RC time constant. So, and as we said that since the capacitance is high, if you're talking about 100 farads, 0.1 change in the ESR is 10, the RC time constant goes by 10 seconds. Okay, so what is shown here as 1 second. So these numbers shown here are basically the time for which they can supply. Okay, so it can supply for 1 second, which means that it should supply all its energy within a second. Okay, but if I increase my, do something to my electrode or to the device where ESR increases by 0.1 ohms, the response time will go to 100 seconds. So the capacitor is meant to provide power for 1 second, but it takes 10 seconds to provide. So that kind of, bad situation one will get into if the ESR is high. Therefore, it is important that ESR is maintained very low for supercapacitor, and ESR therefore becomes an important characterization variable for the supercapacitor. And of course, as we said, that measurement of ESR, so if you have to do, I don't know where, so when you do this galvanostatic charge discharge, as soon as there is a switch over, the potential will drop. And why this potential is dropping? Because when we are charging the capacitor, apart from the voltage of the capacitor, which is Q is equal to CV, an additional voltage is required to drive the current. So the circuit is basically an R followed by the capacitor. So the voltage will be voltage drop across capacitor time plus the voltage drop across resistor, which is ESR. So as soon as we stop charging, the current goes to zero, and the voltage will only be the voltage across the capacitor. So whatever is the voltage drop is essentially the IR, the voltage drop across the ESR, and that becomes a convenient measure of the ESR of the capacitor.
Oh, that's very good one. Any other question, please? Namrata Saxena probably wants to ask some question.
Sir, am I audible?
No. So, if there is no further question, then let us give a big hand to the speaker. So, really, sir, on behalf of the participants and my own behalf, I thank you very much for this. Yeah, Namrata Saxena, probably you want to ask the
Sir,
question?
am I audible?
Yeah, you are audible. You are audible. Yeah. Last question, sir, please.
Yeah.
Please go ahead, Namrata Saxena.
Sir, am I audible?
Yeah, audible. Please go ahead.
Sir, am I audible?
You are audible. Please go ahead.
Okay, sir. Sorry for some disturbance. There may be some network issue. Sir, I would like to ask one question from Shukla sir. That sir, is it possible to use these type of electrodes that you are telling in piezoelectric type of energy harvester?
Yeah, so this is something good that you brought in. So one of the things that I said and left it, hanging in the air without completing it was that people are interested in having capacitors or supercapacitor which have frequency response in multi-thousands of hertz, 20,000, 30,000 hertz. And one of the prime application there is to harvest energy in situations where the frequency of those energy generation is very high. So, for example, some disturbances which are there in the environment. There are converters which can convert that disturbance, mechanical disturbance, to electric power, but there are not fast enough devices of enough strength to absorb them, assimilate them. So this is one of the reasons why there is a lot of interest in supercapacitors which have frequency response in kilohertz and multi-kilohertz. So of course they can be employed in piezoelectric because there it is also expected that the generation of electricity will be at a very high frequency. And these are one application that I can tell you is now all of us here Internet of Things, so IoT based sensor networks. So you will have multiple distributed sensors at distributed locations where there may not be power supply. Okay, for example, you're doing so for some pollution sensor. So you put at different parts of the city. You may put it in just outskirts of the city where maybe the power supply is erratic. And these sensors do not require much power. So if there is a self-generating power, then these IoT will get greatly enhanced. And this is where these kind of supercapacitor could find application. So piezoelectric power generator combining the generator with this as storage is one possible application. You're right.
Okay, sir. Sir, one more question. Sir, as I am working on piezoelectric type of energy harvester for low frequency applications for ambient energy harvesting. So, is it possible to incorporate these electrodes for low frequency applications also?
So if you're talking about titanium oxide based electrode, please remember that low
Sir,
frequency.
ZNO based. Sir, I
Fine.
am asking for a ZNO based energy harvester. So it is possible to incorporate this the electrodes that you are telling, like that carbon one is possible to incorporate instead of gold as it is very costly to
So
do
I see.
electroplating.
a quick answer would be difficult because one has to look at the different aspects. But the point is that uh, if the part required from these electrodes is only to store, okay, there's no other part that they have to play, then most of these electrodes can behave as capacitor up to 5 hertz frequency. So if your generation is below 5 hertz frequency, then they can do. But if gold electrode is also performing some other function, then I'm not sure you can use it. So if storage is the only function, then of course they can be used provided that the frequency of generation is 2 hertz, 3 hertz. Very good electrode only go up to 5 hertz. So that would be a
Oh,
short answer.
okay, okay. Thank you very much.
So finally, let us thank the speaker for this talk. Okay. Thank you very
Thank
much,
you,
sir.
Professor
Thank you
Pandey.
very
Of
much.
course, it was a
Thank
pleasure to be here and deliver the talk. And I will wish all the best to you for the remaining part of the workshop and all the best to all the participants in all their future endeavors. So with that, I'll stop. Thank you and bye.
thank you, sir. Thank you.
Thank you very much, sir.
Thank you, sir. So there is one announcement to all the participants. The next lecture is from Dr. Naresh Kumar, and there is a very special lecture that we are having in the afternoon. So in the afternoon session that we are having very interesting lecture by Professor M. Lakshmanan, who is Bhatnagar Awardee, fellow of all the three academy, fellow of the third Academy of Sciences, and he is having so many awards and prizes, very experienced person. So please don't miss that lecture from 3 to 5, and that will be slightly different from whatsoever that we are having here. So please